Hey guys, hope you are all doing well. Welcome to week 3 session of F1 aerodynamics. In week 1, you saw the basics of aerodynamics and then some terms related to aerodynamics. And you also saw about the airfoil. And in week 2, you saw about the aerodynamics that is specific to an F1 car and rear wing, all those stuff. In week 3, we'll be doing a CFD analysis of a 2D airfoil that is used in the rear wing of an F1 car using ANSYS Fluent. So yeah, we'll be looking the airfoil chosen is S1223. That is the airfoil that has been chosen based on the all the parameters, the suitable parameters and stuff. So we'll be using that. We'll be importing the data from airfoiltool.com. I'll show you how to do that. So yeah, let's get started with it. I'll share my screen. I guess the screen is visible. So yeah, let's get started. Uh, this is the website airfoil database search. So you just have to enter the airfoil number, that is S1223, and then search, and then in group keep it to all, don't keep it to NACA or something, and then search for it. You will receive it. This is S1223IL. This is the airfoil which we'll be using to do CFT. And then to get the coordinates of the two-dimensional airfoil, send it to airfoil plotter. So once you get this, download the CSV file of the coordinate. Yeah, CSV file of the coordinate is downloaded. Then if you open this file, it opens on Excel. So open Excel. So basically, you don't get this. This is what I created. What you get this is name S123 and then airfoil surface. So this is what you'll get. The first two columns A and B is what you get when you open that CSW file that will open on Excel. So what you have to do that to in order to import these coordinates on answers, first you have to convert into a text format that is on Notepad. So how do you do that? Is just first enter all the numbers. Like first enter 11111 starting from the point where x coordinate begins till the last point, and then in the next column enter a number in a serial order from 1 2 3 going till 81. So the 81 points, there'll be 81 points created, which will form the whole structure of the airfoil. And this X and Y coordinate, copy paste it from the here itself. Just this is copy pasting X and Y from here. And then since we are doing two-dimensional analysis, Z coordinate will be 0. And change the decimal places to 3 by using format by right clicking and you going to format cell. There you'll go to number and then you can increase the decimal. Okay, I'll once again show you that. Select this, select this, go to format cell, and then go to numbers, and then yeah, increase the decimal places to 3, and then yeah, now you'll get this. Now copy this and then paste it on your notepad. I have done it already. I've copy pasted and I've pasted it on my notepad. I'll open it. This is what the text file you have generated. So this 1, 1, 2, 3, and then this is X coordinate, Y coordinate, and this Z coordinates. So this is on desktop, so you can directly import it on Ansys. So now we'll go to Ansys. Design, we'll close design modeler now. We'll go to workbench. Yeah, this is workbench, and we'll delete this row first. So we'll be using Ansys Fluent. As you can see from the menu here, there is fluid flow fluent. So we'll be using this. Uh, d- so drag it and then place it here. So this will be formed. And then open the geometry, double click on geometry. Design modeler will open. Yeah. Once the design modeler is open, select an XY plane and then select Z axis so that you'll get XY axis, select two-dimensional view, and then change the units to millimeters, and then first we have to create the point. So we'll be creating point, and then is in millimeter, check the unit, coordinate unit should be millimeters, and then we will select the notepad file, that is the text file from the this thing from so it's saved on desktop. So I'll select this, I'll open it, and then I'll generate it. So as you can see now, my airfoil points have been already imported from the website. Now I have to create the surface, two-dimensional surface. So first, how do you do that is you go to create, you go to concept, and then you create lines from points. So first you have to create the line joining these points. So let's do that. And you have to be careful while doing it. Use control while selecting multiple points. So first I'll select this point, and then I'll use control to select this, and then double click this point, and then select this, and then again click this, select this, and select this. Throughout the whole process, you have to use control, or else you can't select the multiple points. So yeah, you can use the pan option here. So you can pan it so that you can get the clear dimension. The points will be there, it won't move. So as soon as you remove pan option, don't forget to again press control button while selecting the points. That is important. I guess I have covered all the points, selected all of it, and then just apply it and then generate it. So you'll get a points like this. And then once the points are generated, now again go to tool. Now again go to concept. Now now we have created line from points. Now we'll create surface from edges. We'll create the surface. And then again, we have to select all the surface points. Be careful while selecting the points. Again, use control. Should form a closed geometry. Planet. So yeah, now we have selected all the edges. Now we'll apply it. So apply it and then generate it. As you can see, our surface has been generated. This is the surface that been generated with this material. And next we'll be creating a rectangular domain around. Next we'll dimension it so that we can change the dimensions. Now we got a rectangular domain around our airfoil. Then now we'll create again a surface from sketches concept. Surface from sketches. Select these points using control option. Apply, then generate. You can see now a new surface has been formed. Now we have to remove the airfoil part to analyze the CFD, that is the airflow around an airfoil. So we'll do that by using a Boolean option. Go to tools and then use, okay, no, go to create a Boolean. In Boolean, use instead of unite, you have to subtract. So use subtract. Select the body. First, select the surface body, the whole surface body you select, and then apply. And then select the tool body, that is line body plus surface body. Apply. Then generate. Yeah, as you can see, the airfoil material has been removed, and then we have only left with the rectangular domain around it. So that is what we need. So everything's ready right now. And then go, yeah, have been saved. So just to be on safer side, update it, update the geometry, it will get updated. This is a pretty much done on design modeler. Now close the design modeler. We don't have to use design modeler anymore. So yeah, we'll close it and then go to mesh, double click on meshing. Meshing will start. As you can see, you have got a rectangular domain around the airfoil. Now we have to mesh the surface. So before meshing, we'll first select this edge. This is like edge. We'll select this edge and we'll name it. Create a name selection. This will be our inlet. And then select this edge. This will be create a name selection. This will be your top. And then create this, select this edge and then create a name selection. This will be your outlet. And then select this edge, create a name selection, and this will be your bottom. And then you have to again zoom in and then select each surfaces on this body, pan it, and yeah, cursor smart select. Use Yeah, keep panning and then select it. all the points have been selected. So let's click on it, create a name selection, airfoil. Yeah. So you can click on name selection. You can see all inlet, top, outlet, bottom, and airfoil. Now we'll go to meshing part. We'll pan it first. We'll see about meshing, cursor mode. Yeah. So in meshing, go to meshing, insert a method, and then select a geometry, and then apply it, and then use quadrilaterally dominant instead of quad and try. Keep it all quads. Use global setting. Okay, this is pretty much, and then insert an inflation, apply it, smooth transition, maximum layer, put first layer thickness, and then thickness put it as 0.5 mm. Okay, if it's in meter, then put it in 0.005. That is 5 mm. So okay, we need 0.5 mm. So 0.0005, and then maximum layer is increase it to 10, and then let it be this, and then go to mesh normal settings. Element size, you change it to 0.0005 again. That is 0.5 mm. Now generate the mesh. So it will take some time to generate the mesh. We'll see. Yeah, as you can see, now we have meshed. So to see the fineness of the mesh, we'll use skewness. So as you can see, skewness is around zero point 0.6. Anything below zero point 0.5 is good. I mean zero point 0.6, and that too in few places it has reached zero point 0.6. Rest all you can see the minimum skewness, that is the blue color. So it's a fine mesh. So this usually the skewness will be less than 1, but then we have to keep it as small as possible. So we'll try to keep it around zero point 0.5. So it's not a problem. We got around zero point 0.6. It's a good mesh. So meshing, you'll learn about this. This is basically FEA, finite element analysis, breaking the surface into smaller parts, small elements and nodes, and then calculating and then doing calculations on it. So this is FEA. You learn about FEA in your fourth sem in CAM. So that's how CFD works on ANSYS. Since we got our mesh, we can save it. We can update the mesh. Okay, we updated it here. We have generated it, but then we'll have to update the mesh here. So we'll update it. So yeah, meshing is done. We can close it. We can close the setting, meshings, and then setup. Use double precision, and then you start it. I'll cover the whole CFD in this lecture itself, so I won't be available on Sunday, so you can see the recordings and then proceed. So yeah, first this is the this thing setup. Now we have to set up this inlet. This is our outlet. and we can see the foil and meshing that had been displayed here. First, we'll change the units of velocity here. Velocity, where's velocity? Yeah, velocity, and change it to kilometer per hour, and then we'll close it. Okay, next we'll go for models. In models, viscous model, we have to change it. We'll change it to Splot, Almraz. These are the various model available, and then each of them serve a different purpose. If you use K epsilon model, you'll get the flow calculation for the flow, a very good approximation away from the body surface. When you use K omega model, you'll get a good approximation for the results near the airfoil surface. But then Splumart Almraz is another model which we be using here that'll be used for compressible flows and at higher speed. So we'll be using this model. And there are the rest of the models. If you are interested, you can study about them. Okay, and yeah, I don't think there's any changes here apart from this. And then this one equation, and then materials, we'll go to air, open this, and then change it. Air density is not constant, give it as an ideal gas. Whenever we are discussing about airflow, but an airfoil or at supersonic speed or something, we'll usually use ideal gas density, and then viscosity is not constant, change it to Sutherland. All these things are common. Close it. Now I guess again open it to recheck whether all the properties that you have included is there. Yeah, so close it. And then cell zone, boundary conditions, boundary condition, inlet condition you have to give. So inlet condition, velocity inlet. So yeah, we'll define inlet condition. We'll give an inlet velocity of around 200 kilometers per hour. We'll apply. So yeah, this is the only inlet condition. Rest on all remains same. We don't have to do anything about outlet wall or something here. So it's pretty done here in this, and then dynamic mesh reference value. Reference value you have to compute it from inlet. Give that, and then yeah. Apart from this, there's nothing here. And then go to methods and solution. Will be coupled, and then yeah, let it all be whatever the default it is. So the time methods and then controls. We don't have to change anything in that. Report definition, monitors, cell zone, and then go to initialization. You go press hybrid initialization and then initialize. Yeah, this initial hybrid initialization is done, and then we'll run calculation. So number of iteration, give it as 500. But then when the solution converges to a value, it will end before that. Then we'll calculate it. So you can see this it's been getting calculated. Yeah, we'll wait for the calculation done. Usually it'll take around 200 to 50 iterations, I guess. Yeah, as you can see, the calculations got completed. And then we'll go to graphics. We'll go to contours. We'll see the pressure contours of the interior surface, and then we'll display it. Yeah, as you can see here, this is the pressure contours. This is, I mean, the highest point of pressure is at the tip of the airfoil, as you can see the red point, and the least is on the top of the airfoil. Here, the here the pressure is very less, meaning to say the velocity will be very high. This is and the rest of the part below, as you can see, there's an uniform pressure maintained. So there won't be much pressure difference, I guess. So the lift that produce will not affect the F1 cars, or if there's more lift generated, usually the uh, the car might lift off from the ground. So we don't want that, but we know we need some lift. So this ideally this airfoil has been designed on the various other parameters. So this is the pressure contours. When you can see velocity contours, it'll be something like this. As we saw here, the pressure was less, but then the velocity is highest. That we can prove it by Bernoulli's law. And you can see at the tip point, velocity is the least, and whereas the pressure point is high. These are the main things we have to concentrate on this. Yeah, we'll close this and then we'll go to post CFT. Yeah, this is done. We'll close Fluent. We'll okay. Okay, setup is done. Solution is done. Then we'll go to results. We'll see the results. We'll again see the contours. Yeah, this is post CFT and press Z axis. You'll get two-dimensional wireframe. This is the wireframe model. Now we'll go here. This is contour. You can see a contour one will be created. All domains, location, I'll give symmetry one, the whole thing. Pressure global and number of contours, I'll increase it to 20 and then I'll apply. As you can see, this is the pressure contour. This is the pressure contour, and yeah, as we saw before, the highest pressure is this red dot here in front of the tip of the airfoil, and least, as you can see, the dark blue region on the top of an airfoil. So yeah, this is the pressure contour, and then we'll create another contour of all domains, but then here we'll go for velocity and then symmetry one velocity, and then here also we'll increase the combust to 20. And then deselect this contour one. So then contour, just select contour two. This will be purely velocity contour. And same analysis as we did before. Highest velocity on the top of airfoil because the pressure is very low. And then the velocity at the tip of the airfoil is least given that the pressure is highest. And this is the contours of this. And then if you want a streamline flow, create a streamline, 3D streamline all domain starting from, okay, we'll start from inlet if you want. We'll start from inlet, or 3D, and then apply. Yeah, when you put from inlet, this is what it seems like. If you want it from the surface body, you can put select surface body and then apply. From surface body, this is how the velocity streamline looks like. So yeah, you can put different stuff and then you can apply it. So this is about a symmetry, about the symmetric one. So then if you do the animation of it, you can see animation of streamline one. So you can see this is how the contrast moves. Basically, this is the CFD analysis. Mm, and this is how will be done. These are the results we'll be analyzing. So basically, you will be given another airfoil or probably a body where you will do the same analysis and then give the contours and streamline. So yeah, pretty much that is it from this from here. Yeah, this is yeah, this is the end of the week 3 session. I guess you have learnt about CFT on ANSYS. If you have any doubts, you can ask me. You can post your doubts on Teams or contact us through my mail ID. So yeah, guys, thank you. I'll be ending it.